to speak about some recent work which Mike also alluded to at the start on how to incentivize data sharing and in these collaborative learning space. This is joint work with Vensho and with Mike, and it's still ongoing work, and I would love to hear more input from all of you. Okay, so let me just skip this. So this question of incentives and fairness has sort of risen up over the morning multiple times, and there has been tremendous interest in these for reasonable reasons. But I think pretty simple basic question is still unanswered in this, and I want to sort of like try and motivate some of the questions which I have, and hopefully motivate more people to work in this space. So let's think of the setting where there's two agents. Let's call them Alice and Bob. They want to solve some task. It's an identical task. They both contribute, say, equal data. Say 40, whatever 40 means. And they both we do some collaborative learning for more training with some of these amazing methods which we have learned today. And say they both get back a model which has 80% accuracy. Everyone's happy. So it's probably a good scheme. It is fair and incentive compatible at least intuitively. But now suppose that Alice only gives 10 data points and Bob gives 70 data points. Then we do the same thing. So the net amount of data is still 80. So we still do the same thing. And we get a model. They both end up with a model with 80%. So is this a good scheme? Intuitively, at least, no. And there is some intuitive feeling that this is an unfair, or it's not. We're not incentivizing correctly, because this means that Alice can get away with just giving 10 data points. Okay, so how about this? We're in the exact same setting, but Alice gets 30%. So we do some training algorithm, like this is some magical black box. Alice gets 30%, Bob gets 80%. Is this a good scheme? I don't know. Like how much should we actually penalize Alice for the 30 for contributing 7 times less amount of data? It's clear that we should penalize, but exactly how much, and how do we think about this question? And suppose we're in the same setting. Alice gives 10, Bob gives 70. Both get an 80% accuracy back. But now Alice's cost for generating 1 data point is 7, and Bob's cost for generating 1 data point is 1. So the net cost for both is the same. So for Alice generates 10 data points with cost 7, Bob generates 70 with cost 1. They both are paying equal cost. So is this a good scheme? Incentives actually says no, because we should be incentivizing Alice to reduce her cost. But fairness maybe says yes, because both are sort of putting in equal amount of cost. Just to illustrate like the complexity of these issues, even with this extremely simple toy setting, right? Suppose these Alice and Bobs now have different tasks. So they want to train different, they have different goals, but based on the same starting data sets. So they both give equal data, 40 data points. But now Alice gets back 30%, Bob gets 80%. This 30% is just because Alice's task is just much harder to solve. So is this fair? Is this a good scheme? Is this incentive compatible? So if you use your typical definition of fairness, or at least some notions of fairness, you would say this is not fair because Alice is actually getting much less out of it than Bob is. But we are doing the best we can. Like if both Alice and Bob are using complete data available to everyone. It's just the problem is harder. So all these examples are just to sort of illustrate this this feeling that general answers pretty much seem impossible in this space of thinking about incentives and fairness in this collaborative learning. And whenever general answers seem impossible, it's usually because the problem is ill-posed. And I think the goal should be to sort of go back and ask, why do we want fairness? Why do we want incentives in our mechanism? And we usually have some goals before we start. So we want to ensure that the agents join. We want to ensure the agent contribute. So we want everyone to sort of contribute as much as possible. We want everyone to sort of join our platform. we want our platform to get picked than over our competitors. So in general, we may have many goals. What we're trying to do, why we're using these fairness as incentive is because we want to sort of influence the behavior of people who are participating to achieve some goals we have. This may be obvious, but but it directly implies that we need to first of all define our goal. We can't just say fairness or incentive as the starting goal. At least that's my opinion. These examples hopefully motivate that we really need to define a goal, which is before we say whether an algorithm is incentive compatible or it's fair. And we also need to sort of model the agent's behavior. If the whole game is to influence the behavior to achieve goals, we need to define what those goals are. And we need to model behavior so that we know if we're influencing them. So this is going to be like so I'm going to talk about some work on these two aspects. Okay, so how do you model the behavior of an agent? Here's a simple example. I'll work through some toy settings for everyone here. We assume that only the size of the data set matters. And the value extracted from this data is some simple function which looks like this. It's 0 up to some threshold. So if you just are given 10 data points, it's probably useless. But after that, it's nice and it's increasing, concave, and bounded. This is the only assumption we're going to make. And what is the cost of generating this data? Let's say it's a simple function which is like a linear. So if you have m data points, it's c times m. It's possible to generalize this much more, but let's stick with this simple setting for now. Specifically, but each agent may have different values and different costs. Okay, so what is the utility the agent gets from going through this process of collecting data? It's whatever the value they can extract from the data minus the cost. It's very simple stuff. The curve looks like something on the left. So up to the threshold, you're just collecting data without getting anything, so your utility decreases. Then it increases, and at some point you saturate and it decreases. So in this particular case, the utility is sort of maximized at 300 data points, and that's what this Alice would sort of end up collecting if she was working on her own. But this is a low cost setting. You can also have a setting where your utility increases, but it never crosses the threshold of 0. So in this case, if you're in a high cost setting, basically the optimal amount of data to collect if you're working on your own is 0. It's maximized at 0. And this is a problem which is sort of too hard or too expensive to solve alone. And this is really the kind of problems we want to tackle with these collaborative learning frameworks, where these problems are just too hard for a single person to solve on their own. And we want sort of people to come together and solve that. Okay. So now we also need to sort of model this the collaborative learning mechanism. Suppose each of the participants contributes some amount of data. So let's call it MI. I'm defining a collaborative learning mechanism as some black box process which can take all these contributions and it'll run whatever a personalized collaborative learning algorithm, which state-of-the-art method, and returns some models to these agents with some valuations we want to be in. So just mathematically, it's the mechanism M to the ith agent given contributions M1 to Mn returns some value to the ith agent. There's some obvious properties this needs to satisfy. It needs to be feasible. So you cannot give more value than what the net data you've collected so far. So a mechanism needs to be feasible. It needs to satisfy this unusual rationality, which Nika referred to earlier, which is that there should be some benefit to participating, and there's some you can describe with this language some properties of these mechanisms. And to model, so we have like a pretty general theorem which states that for almost any reasonable mechanisms M, there exists a pure Nash equilibrium of contributions such that no agents wants to deviate. So if you're not familiar with any of these concepts, doesn't matter. The upshot is that given a mechanism M, we can predict using this theorem, we can actually predict what the behavior is going to be. So given a mechanism, we know how people are going to behave. And so this is how we can model the agent's behavior. What's the goal? Well, a reasonable goal is to say we want to build a platform where the value is maximized. So everyone's contributing as much as is possible, with the net result that the value of which each of the agents was able to extract out of the platform, the sum is maximized. So, or in simple terms, the net amount of data collected by the platform is maximized. So we can define this formally. For a given mechanism M, we can define a set. We know that there is an equilibrium contribution, so we can predict what the contributions are going to be. For these contributions, let's say these are the equilibrium contributions. What is the mechanism which will ensure maximum equilibrium contributions? So we've sort of modeled what the behavior of the agents is. We've also defined our goal. So now we are in a good space to sort of actually go back and look at some of the mechanisms we've been hearing about. So just to sort of take a look at the standard federated learning setup. So here, the mechanism just shares the full data with everyone without taking care of any sort of incentives or anything. That's basically captured by saying you collect data, you get whatever you can extract from this to every agent, every participant. What happens in this setup? Basically, we'll see some catastrophic free riding. Essentially, we can prove that all but one of the agent will contribute nothing. And this one agent will be the only one who's contributing data. And everyone else is just sort of using the data for free. This is probably intuitive that if someone else is contributing data, why should I? If this data is already going to be useful for me, and if I'm guaranteed that my data, they're going to be sharing this data with me, then this sort of free riding behavior is to be expected. It's mathematically quite straightforward to prove this, but I think it has some interesting implications for policy and as was referred to earlier for defining these laws around these data sharing. There's these data sharing regulations, data portability regulations, which you're probably familiar with, which basically says that every internet company needs to actually allow each one of us to download our data from the platform and re-upload it somewhere else, which basically means that data sharing is sort of mandated. So under such a mandate, it's possible that we'll see a lot of this free riding behavior. And perhaps more troubling perhaps more troubling is if we go back to this case where we looked at this high cost setting, where no single agent can actually solve the problem. Or we can prove that every of the participant will expect everyone else to free ride, and so no one will actually end up contributing anything. So everyone will contribute zero. This is basically, if everyone worked together, they could have shared the cost and solved the problem. But because everyone expects everyone else to free ride, you sort of have this failure of collaboration. And so then we can, okay, what are the other possible mechanisms?
Sorry, I just wanted to understand. Is this like in the perfect beige kind of perspective, saying that because I expect everybody else to do this?
This is, so I'm being informal here. This is so far everything is in full information setting.
I see.
So clearly the solution is we want to penalize an agent who is contributing less. So one possible way is you look at what the maximum amount of contribution is from everyone else. And you sort of, if your contribution is less than that, you penalize using this form. This seems to be a reasonable method to do. You can have this parameter P. This is also motivated by some fairness type methods. You could have many different variations of this. Why the amount of data? You can use you can penalize proportional to the value, or you can use these more complicated notions like Shapley values. And these are all reasonable, potentially reasonable methods. Which of these should we use? We can actually use our theory to sort of simulate what would happen with each of these settings. the exact results don't really matter, but essentially we can actually compare what we can figure out what will happen with different choices of these mechanisms, with different choices of these exponents. And these simulations show that under these conditions, at least, the proportional value mechanism is not so great. The Shapley one and the simpler data one works well when the exponent is like roughly 0.8, 0.9, which is, these are very non-trivial observations which came out of some really simple modeling. In fact, we can prove that there exists an optimal, very simple mechanism which is like optimal and maximizes the data. I don't really want to get into the details here, but the upshot is trying to actually model what the behavior is and defining the goals allows you to sort of do these simulations and the theory in the space of mechanisms. And we can do more. We can actually analyze these fairness concerns as well, as I was referring to earlier. So imagine that there's one group of agents who have a cost of collecting data, which is 10. A second group which has a cost of collecting data, which is 20. We could ignore this difference in costs and say we will still penalize someone who's collecting less amount of data. Or we can also just use this optimal mechanism, which is sort of hinted at earlier. And we can see what happens. So if we use this scheme which sort of ignores this difference in the cost, at equilibrium, the penalization is so stringent that all the high cost agents will sort of drop out. It's not in their interest to actually take part in the mechanism at all. They just drop out. So this is hurting both the system as well as those agents. Whereas under the second mechanism, things seem more better. So we can also ask, okay, what happens? So everything so far assume that we sort of actually know what the value of the data which everyone has. So we assumed we knew what this valuations was. And I think as there was questions earlier today, this is a big challenge of how do you actually compute these values. I don't have a full answer, but at least to some specific extent. So if we don't know the values, but we know roughly what kinds they are, or if we don't know the cost, but we sort of roughly have an idea of how they look like, we can use these contract theory based ideas to make sure that the mechanism we are designing is truth revealing in some sense. I won't go into the details here, but my goal with this is just to say that there's a lot of many open questions in this. And I think it's a great opportunity to sort of lay the foundations in this new area with some rigorous guarantees. And with this I want to sort of end it and just with some simple advertisements to some recent work. So federated learning is probably has dire needs of some real world benchmarking. I think there's going to be some talk on this tomorrow as well, but not on this, but on benchmarking tomorrow as well maybe. But this is one attempt at this. We need your help. Please reach out. This is in collaboration with the company, with many folk and some folk in the audience right now. Questions around all the usual questions which we're discussing need to be investigated on these real world data sets. And a second plug is we have if you're familiar with Scaffold, we have a new method which seems to work amazingly well. It's upcoming at NeurIPS. Just a teaser here. In below, so this is like, here is like all these standard methods, and we start our method at different points, and you can immediately see the shoot up in the performance. So a simple plugin. If you're interested, reach out. And yeah, and thank you. Any questions? Yes.
Yeah, I mean, it's a very interesting work because you spend a lot of time in modeling, and I think that's a good modeling if you capture settings where you have organization want to cooperate, but they have competition. So this is a very good modeling. The assumption holds here perfectly good. But for because I come from another community, we have other co-science, like users, but other communities are really, it's harm and privacy that hold them from sharing. Is there a way to capture this, like guarantees in the way you formulate this type?
Definitely. So there's two questions there. One is, can we capture? So that whenever we share data, sharing data comes with some inherent risk. So there is a question here of how to sort of model this risk. So one standard way is to say each data point you share carries with it some X percentage of risk. So the more data you share, the more risk it carries. So you can think of this as a simple cost of data sharing, and that sort of perfectly plugs in with our model. But yeah, it's a very good question of how do you model this risk. And there aren't any general answers here. So if you look at this is not really anything new, what I've said. Most of these.
For example, if models generalize well and you guarantee that nothing about me can be inferior personally, I'm happy to share all my data, but that's a harder thing. If these kind of guarantees at least also can be captured.
Combining these differential privacy with guarantees with these into these frameworks is an active area and something which is super interesting. I'm not sure how to capture. So the cryptographic guarantees, I think, are more. So differential privacy still is never like a 0-1 guarantee. There's always some amount of risk, whereas cryptographic guarantees are really much more 0-1, which is they're like completely secure or exponentially secure or whatever. So those are probably not. This is not a good tool to sort of capture those, but privacy laws and these kind of things, I think, are very compatible with this. I think.
Yeah, there's a line of work John Ducci and Martin Wainwright have where we trade off statistical loss risk against differential privacy, and you can operate on a curve, and you can decide, oh, for that problem, you want my medical data because you're studying a disease that runs in my family. I'll turn up the differential privacy knob a certain level. If you're just trying to use it for demographics or something, I'll turn down the knob. We can actually know for that. So that's a whole line of work, but and then doing that with incentives and all is another issue. But yeah, I like to think of differential privacy as just another knob that people will get used to, like euros. How many euros of loss do I have? And what's the trade-off? I mean, if you ask me for my genome and you say I'll give you $5 million, you can have my genome.
And harm, can we capture that also?
Well, I think humans will, give humans the ability to decide how much harm. Harm is a trade-off. If you give me $5 million, I'll take a lot of privacy loss because I get so much out of that, and so let me kind of associate how much risk I'm willing to tolerate for how much gain. And it depends on the loss function that you're using. You should tell me what you're studying, why you want my data. And that should be.
Or later, where is this model used? This probably knows more about technical solutions.
Yeah, absolutely. That's right. But yeah, the 0-1 notions of privacy, I think, are just maybe they're okay for other situations, but that's the lawyers kind of like it. But it's not, I think, for our field the right thing. It should be another thing you trade off with accuracy, with time, with all the other kind of things that we care about. Human beings don't need absolute privacy; they need gains for their privacy loss.
I don't agree cryptography is a 0-1. I think it's also like zero knowledge proofs is not 0-1. It's just minimization and purpose limitation more. So there are different tools like encryption, yes, 0-1, but secure computation or zero knowledge proofs it's actually a spectrum and limiting scope actually more than just.
I need to hear more about that maybe offline because I'm not so aware of that. That's a cool way to think. So it's all about trade-offs. Indeed, if we can make everything less 0-1, then we can trade them off and have theories that actually have the trade-off embedded in the theorem. Then you can set things and tell the designer how to set things.
Yeah. If there are no more questions, we'll break for lunch now.